My name is Rachel A. Rosen, and I'm an associate professor at Columbia University in the Department of Physics. As a kid, I was sort of enamored with Sally Ride, so I saw her on TV when I was, maybe even on some PBS program or something when I was a kid, and was really excited about what she was doing. The focus of my research is on quantum field theory and applications of quantum field theory to particle physics and gravity, and occasionally to condensed matter systems as well. The black hole information paradox is sort of an outstanding problem. If you threw a dictionary into a fire, even if it burned up, if somehow you could collect everything that was emitted, you could reconstruct the dictionary. But it's an open question with black holes. I've been looking at, from particle physics point of view, alternative theories of gravity. So one in particular goes by the name of massive gravity, and it's the theory in which the graviton, the particle that conveys the gravitational force, has a small mass. And so this is in contrast to Einstein's general relativity, where the particle that conveys the gravitational force is massless. So one thing that I'm very interested in is, what do black holes look like in this alternative theory of gravity? So one of the main things that seems to happen is that either you have to give up this assumption of time independence and your black holes have to have some time dependence, or maybe you have to give up the notion instead of spherical symmetry, and black holes in massive gravity might inherently have to be rotating, something like that. There's the question of what's the correct gravitational theory at incredibly short distances, where quantum effects become important. So this is what string theory addresses. The third sort of open question related to gravity is the explanation of the cosmic expansion of the universe. So why is the cosmic expansion accelerating in particular? And so it's possible, it's likely that this is just some vacuum energy, some cosmological constant, but in which case you really want to understand what the value of the cosmological constant is. And so all three of these problems are related to gravity. Day to day, I have a lot of different responsibilities, teaching and meeting with students, and writing grant applications, and then the actual part that really motivates me is the research part as well. And so that often involves anything from meeting with collaborators and discussing new ideas that we have, to looking for papers and reading papers that might be related to what we're interested in. The fact that you can use mathematics to explain, actual phenomena that you see in the real world, that's always felt kind of magical to me. By studying quantum field theory and particle physics and gravity, you're sort of getting at the most, fundamental questions about our universe.